19 chapters, and we discussed earlier why we need the kinetic theory of gases. So, and then we were on the Avogadro number, molar ratios, but then suddenly internet connection switched off, so we stopped there. So today we are going to discuss about the microscopic behavior, why we need Avogadro number. So the question is, we will use it in our normal daily life practice? No. In daily life practices, we never use the microscopic behavior. We normally use the macroscopic behavior of the gases. It is just like, okay, if you have a gas within a tire, if tire is a flat and if tire has a air inside it, so it is a macroscopic behavior rather than the microscopic behavior. Microscopic behavior deals with the situation where we have concern with the atomic or the molecular states of the gases. Okay, like let's suppose if you want to calculate or modify the structure of composite materials, in that scenario we usually use the Avogadro number, or we usually deal with the Avogadro number, where we have a molar mass and other things like that. We want to uh, dope certain material into the certain, let's suppose in a simple way you can say that normally we have a silicon, n-type silicon, okay, for n-type silicon or the p-type silicon, and in that scenario we deal with the molar mass, okay, during the fabrication process or the synthesis process. At that time we should be familiar with the molar masses of each content, pure germanium and that of the n-type germanium, or the number of the dopants, how much dopants we add, how much the number of atoms roughly counted for in n-type material from the fifth group, or in the p-type material from the third group. So here, just for the sake of information, they have given us the Avogadro number or the molar mass. In the overall study of this subject, you will deal with the microscopic behavior, like if there is a gas in a chamber and if it is moving upward, if it is moving downward, it is isothermal process, isoporic process, something like that. Okay, so overall we will discuss about the kinetic theory of gases with respect to the macroscopic behavior. So here, just we will discuss certain things and then we will move toward the microscopic behavior. So Avogadro number, we are all familiar with Avogadro number. What is Avogadro number? It is 6.02 into 10 power 23. Okay, so this is the Avogadro number, and we all studied in the FSC in the metric. Okay, okay. What is the value of the Avogadro number? So why we need Avogadro number? So again, the thing is that when we want to measure the our sample, again microscopically, when we deal with our samples, we measure their sizes in terms of moles. Okay, so when we are dealing with the moles, we should be familiar what number of atoms it has, or the what number of molecules it has. So the unit of the mole, the definition of the mole is, the one mole is the number of atoms in a 12 gram of carbon 12. मतलब normally जब it is a base unit, and we do know that all the base units are optimized on the certain conditions के length इतनी है, तो एक certain material length at this temperature, what would be the length of that material? ठीक है, we take it as a optimized parameter, and we do measurements accordingly. In the same way, we deal with the mass, and in the same way we deal with the current, and so on. So these are the optimized parameters. ठीक है, so for the mole, it is the one mole is the number of atoms in a 12 gram of sample. ठीक है, or the question is कि how many number of atoms in a mole. ठीक है, okay, I am telling you कि ठीक है जी, one mole is the number of atoms in a 12 gram of sample of carbon atoms. So the question is how many atoms are the molecules are in a single mole. सॉरी एक सेकंड बेटा, मैं एडमिट कर लूं, 2-3 स्टूडेंट्स हो गए. ओके, In the previous chapter, we skipped that an article which was not a part of your course. Okay, so the Avogadro number is basically 6.02 in 10 power 23 atoms per mole. ठीक है जी, where mole represents the inverse mole or per mole. ठीक है, so this Na is basically called as the Avogadro number, and it is based upon the Italian scientist Amedeo Avogadro, who suggested that all gases occupying the same volume under the same conditions of temperature and pressure contain the same number of atoms or molecules. Okay. Up ideal gas. Last time someone was asking me, okay, what would be the ideal gas? ठीक है, someone asked me what would be the ideal gas. अच्छा, इस चीज को थोड़ा सा आपने ज़हन में रखना है कि the last statement which I have told you, that all the gases, ये याद रखना है आपने, all the gases under the same conditions of temperature and pressure contains almost same number of atoms or molecules. Okay, and the thing is that at lower densities, ठीक है, the difference between the number of atoms almost, मतलब उसने word use किया है almost. Okay, so at lower densities, when you have low density of the molecules, you can say that you have very minute molecules in a very big gas chamber. So then you will say, okay, at that time, all type of gases, whether it is oxygen, nitrogen, hydrogen, they have the same number of atoms. Okay, so just remember this. Later on, we will use this concept, and you will get a clear idea. Okay, so last time someone was asking me, what is an ideal gas? Okay, ideal gas is again a gas. Normally, we say that it is a gas in which the molecules are very far apart, and they have no collisions with each other. ठीक है, means that they have little effect on each other. It is just like in the previous lectures, once I told you that it is just like billiard balls. ठीक है, when you have a billiard ball and you will hit them with a white ball, ठीक है, obviously what will happen when a white ball strikes with another ball, it transfers its energy while the other ball starts moving, and the white balls, it loses its momentum. Okay, so in the same way, if you are talking about the ideal gas, so you have to assume in the ideal gas that there is no effect of the collisions. Normally in our calculations, we assume that every gas is ideal. Okay, we basically exclude the factor that they are striking with each other. We only take into the account how many gases, how the effect of gases are on the walls of the container or the chamber and something like that. ठीक है, and what is the behavior between them, we usually ignore that. ठीक है, so in the same way when in actual case the ideal gas can be defined as a gas in which the molecules or the atoms are far apart, so that they have no effect upon they have no effect of the collisions that are occurring within them. Means that they are not colliding with each other, they are just colliding with the walls of a chamber or a container. ठीक है, अच्छा, up to this point any question beta, is it clear? Any question अगर किसी का हो?
जी सर, नहीं क्लियर है.
अच्छा, अब ठीक है, नेक्स्ट स्टेप इज सेइंग के नंबर ऑफ मोल्स. ठीक है, फर्स्ट लाइन contained in a sample of any substance. ठीक है, कि अगर आपके पास आपने कैलकुलेट करना है कि you have a gas within a tire and you want to find out that how many moles this gas within a tire has. So for that purpose we use the equation 19(2), which is basically ratio of the number of molecules in a samples to the number of a molecules in a 1 mole. Means that this is if you want to calculate the number of moles. So this small n is basically number of moles. So in a tire you want to know, okay, how many moles with respect to the molar mass, you want to know how much moles of a gas exist within the tire. So for that purpose, you will use the ratio of the number of molecules in the tire to the number of molecules in 1 mole. So under the denominator equation, denominator would always be 6.02 into 10 power 23. Okay, so this is the Avogadro number. While on the numerator, okay, it is basically the number of molecules in a sample. So here he's saying, okay, you should get a clear idea. You should not confuse what a small n means, what a capital N means, and what an A means. Okay. अच्छा, again कहता है कि we can also find the number of moles in a samples from the mass of a samples. ठीक है. Basically, what I am currently doing in my research, or what I have done in my research, is that I synthesized energy materials. In the PhD, I synthesized the energy materials for the solid oxide fuel cell for the generation of electricity. ठीक है. So currently, matlab, I am dealing with the chemical synthesis of the materials, and in the chemical synthesis, I deal with the molar mass, and I deal with the mass of a sample. I convert 1 mole is equal to the okay जी इतने grams है, ठीक है, molar mass in point, and then I will use another dopant material to enhance its properties, ठीक है, and then to find out okay to find out or to optimize those properties, ठीक है. So in my experiment or the chemical synthesis, or you can say that in the industry, we deal with the mass of the samples, and we take the molar mass of a material, ठीक है. And how we can take it again, this is the number of the moles, this is the mass of the sample, ठीक है जी, and this is the molecular mass of the material. जो भी आपके पास कोई मॉलिक्यूल है, लेट्स सपोज मैं कहता हूँ जी ओके मेरे पास कोई मटेरियल है, जस्ट फॉर द सेक कंपोजिट मटेरियल है, बेरियम सिरेट है. बेरियम सिरेट जो है वो जो है उसका मॉलिक्यूलर मास कितना होगा, तो एक एटम का मैं मॉलिक्यूलर मास ले लूंगा, या H2O ले लें जस्ट फॉर द सेक ऑफ द फन. आप ये ले लें कि आपके पास एक केमिकल फॉर्म है, ठीक है, सॉलिड फॉर्म के अंदर आपके पास एक केमिकल पाउडर लिया हुआ है, तो मॉलिक्यूलर मास उसका कितना होगा, 1 जो आपका मोल है, इट वुड बी इक्वल टू 1 मॉलिक्यूल का जो मास है, इट वुड बी इक्वल टू मॉलिक्यूलर वेट, जो कि आप H2 कितने हैं, यानी 2 इसका 2 ये हो जाएंगे इनटू O आ जाएगा 16, वो तो टोटल जो हो जाएगा वो 18 ग्राम जो है उसका वेट बन जाएगा, ठीक है. सो ये मॉलिक्यूल वी डील विद द बेसिकली अगेन विद द केमिकल सिंथेसिस, इट हैज अ मेजर रोल, ठीक है. बाय smaller variation in the quantity, you can get a quite different results than you are than desired, ठीक है. So these are the things that it deals, ठीक है. अब ये आपके पास क्या है कि 1 moles here again you can say that this is the molecular mass, and this molecular mass .02 into 10 power 23, ठीक है. ये small m आपका molecular mass है, ये आपका molar mass है, and upon the top in the numerator you have the mass of the sample, ठीक हो गया. So again आपके पास क्या है कि आप इस फैक्ट को यूज करते हैं कि from where you are getting the molar mass, so molar mass is equal to this one, ठीक हो गया. So up to this point any question बेटा? किसी का क्वेश्चन हो तो वो भी कर सकता है. आप सारों को नींद तो नहीं आ रही?
नो सर.
नो सर.
अच्छा चलें. अच्छा अब सेकेंडली ये है कि आपकी गुड न्यूज है मजीद कि आपकी छुट्टियां बढ़ गई हुई हैं, कि बैड न्यूज है? व्हाट डू यू थिंक?
सर अच्छा है, रमजान घर हो जाएगा घर वालों के साथ.
बैड न्यूज़ है सर.
बैड न्यूज़ सर.
बैड न्यूज है. अच्छा
यस सर.
एक बात मैं तुम्हें बताऊं कि आप जब हॉस्टल लाइफ में होते हैं, स्पेशली हॉस्टल लाइफ, ठीक है, सो रमजान इज अ वेरी डिफरेंट स्टोरी. मतलब बहुत मजे की चीज होती है कि मतलब आप बैठे होते हैं मेस के अंदर सुबह सवेरे, मतलब हॉस्टल लाइट्स जो हैं, मतलब उनके लिए हम लोग थे व्हेन वी वर स्टूडेंट्स थे, ठीक है जी, हम लोगों की ड्यूटियां लगी होती थी. अच्छा ग्रुप जा रहा है, इकट्ठा जा रहा है, अच्छा जी कोई बच्चा बैठ गया मैथ्स में, कोई उठा नहीं है, उसको नॉक कर रहे हैं जी जाके, वो देन शोर शराबा हुआ है सारा, मैथ्स में रश होता है अचानक, ठीक है। देन वी यूज्ड टू गो टू द कैंटीन, ठीक है, चाय पीने जा रहे हैं, मतलब बड़ा डिफरेंट है, मतलब सिनेरियो आप एंजॉय करते। बट एनी हाउ कि बेटा ये है कि करंटली आई वाज लुकिंग दी स्टैट्स के they were saying it is about in the last week it's about 18%, matlab 18 out of 100 were diagnosed with corona, and now I think it has increased. And in Islamabad they are saying they have randomly tested 100 pupils, and out of 100 39% persons were carrying corona, ठीक है। So currently be careful बेटा, अगेन बी केयरफुल, थोड़ी बहुत चीजें जो हैं वो प्रिकॉशनरी मेजर्स के साथ लें, अब मास्क पहने, मतलब इन माय ओपिनियन के जो मैंने देखा है अभी तक करंटली फ्रॉम द लास्ट 1 year के ड्यूरिंग रेनी सीजन और द ह्यूमिड एनवायरनमेंट द स्प्रेड ऑफ द कोविड डिक्रीज्ड, ठीक है। यू कैन सी फ्रॉम द लास्ट मार्च टू दिस मार्च whenever there was rainy season, there was decrease in the COVID cases. So currently this कह लें कि January to March, ठीक है, you got almost 31% less rains compared to last year and the year before that almost. Okay, so it is now spreading at a quick pace, so be careful about that. Acha, now coming toward the ideal gases, ठीक है, again in the very start he is saying that our goal in this chapter is to explain the microscopic properties of the gases, ठीक है, rather than the microscopic properties which we discussed, which we just discussed. So microscopic properties include the pressure and temperature, ठीक है जी। एक सेकंड बेटा, अभी भी कोई एडमिट होने आ रहा है, चलें। सो माइक्रोस्कोपिक बिहेवियर ऑफ एनी गैस, ठीक है, क्या होगा कि वी वांट टू डील विद दैट, ठीक है। अब कहते हैं कि एज आई वाज टेलिंग यू दैट कि एक्सपेरिमेंट, मतलब आपका जो आइडियल गैस है, आइडियल गैस, ठीक है, इट इज जस्ट ए गैस, ठीक है, ठीक है, इन विच द एटम्स आर क्वाइट, you can say spread at a very large volume, or means that they have a very small density, ठीक है। So just to avoid the collisions between them, so they have the minimal effect upon each other, ठीक है। So they are saying in this line, in the bottom line, they are saying कि एक सेकंड बेटा, रेड कलर, ये एक सेकंड, ये जो है आपका इस लाइंस के अंदर ये कह रहे हैं कि लेट्स सपोज एक्सपेरिमेंट्स डेटा हैव शोन दैट इफ यू हैव टेकन 1 mole of different gases in a boxes of identical volume and बेटा किसी का माइक ऑन है, माइक 38, चलो अच्छा। So you have taken 1 mole of different gases like hydrogen, nitrogen, oxygen, whatsoever. You have 3 different gases, ठीक है, and you have these gases in identical volume, means that in identical boxes, ठीक है, and have the same temperature of all those boxes, ठीक है, and they have the same pressure, ठीक है। So क्या कहते हैं कि एट लो डेंसिटीज, ठीक हो गया, द डिफरेंस टेंड्स टू डिसअपीयर, ठीक है। डिफरेंस जो होता है, देयर विल बी नो डिफरेंस, दे विल हैव ऑलमोस्ट सेम नंबर ऑफ एटम्स, ठीक है। फर्दर कहता है कि एक्सपेरिमेंट शोज, अब आपके पास जो इक्वेशन है जो आप लोगों ने एफएससी में पढ़ी थी, ठीक है, फॉर रियल गैसेस और द आइडियल गैसेस, ठीक है, एट लो डेंसिटीज। लो डेंसिटीज पे जब भी हम बात करेंगे वी आर टॉकिंग अबाउट द आइडियल गैस। जब हम हाई डेंसिटी की बात करते हैं तो वी आर टॉकिंग अबाउट द real gases. So normally when we do our calculations, we deal with the lower densities rather than the higher densities. So if you want to check the parameters or the different properties of the gas on a macroscopic behavior, first you will check the properties at the lower densities to make it an ideal gas. ठीक है, when you will make it an ideal gas, you will use the equation of the ideal gas, which is PV is equal to nRT. So how you can attain the ideal gas? Again, I am telling you that you will deal with the lower densities. ठीक है, so again this is the ideal gas law, PV is equal to nRT. ठीक है, where R is the gas constant, ठीक है, T is the temperature, ठीक है, आपके पास N is the number of the mole of the gases, P is the pressure, absolute pressure means that atmospheric pressure, ठीक है, we are not talking about the gauge pressure कि आपके पास जो गेज प्रेशर है उसको डील नहीं करना कि करंटली कितना प्रेशर है, वी आर टॉकिंग अबाउट द एटमॉस्फेरिक प्रेशर, ठीक है. So these are the questions that they have, and V is the volume here. So we can also rewrite the gas constant with respect to the Boltzmann's constant, and for that purpose, what you are going to do is you will divide this gas constant with the Avogadro number, and you will be able to get the Boltzmann constant. In some equations, you will see it as a Boltzmann constant, but mostly you will write it as a gas constant. So a value of gas constant is 8.31 joules per mole carbon, while in the Boltzmann constant you have a value of 1.38 in 10 power minus 23. So we can also write the above equation, ठीक है. This shows that gas constant is equal to, this equation shows that gas constant would be equal to K into Na, where K is the Boltzmann constant, Na is the Avogadro number, ठीक है. So equation again he used the, आपके पास Na जो है from 19 to equation जो है from here he got the Na which is equal to small n capital N. So he put the value of here in this equation small n is equal to capital N over Na, ठीक है. और आपके पास जो इक्वेशन जो है आपके पास ये बनेगी nr is equal to capital Nk, ठीक है. So how you got this equation? nr कैसे आई आपके पास? How you got this one? मुझे तो समझ नहीं आई, आप लाइक बच्चे हैं, आप बताएं. See here बेटा, K capital Na, okay. So this was the question. So here when we were talking about the number of moles, so we write it as, एक second बेटा, 10 minutes रह गए थे, just like this ones, okay. So it means that Na can be written as capital N, okay. So it is just like this one, ठीक हो गया. So if I will multiply the top equation with small n, so the top equation will equal to R is equal to K N Na. So this equation is equal, this thing is equal to what? Capital N. So I will write it as like this one. So this is how this equation we got, 19.8. Is it clear beta?
Yes sir.
Should I solve?
सर दोबारा बता देना.
अच्छा, this is a gas constant, ठीक है, this is the Boltzmann constant, and this is the Avogadro number. So this is equation which we got here. ये आपके पास जो equation आई यहाँ पे, at this point we got this equation, ठीक है, ये आई. अच्छा, so अब 19.2 equation when we were talking about the molar mass here, so this equation was equal to what? ये equation आपकी ये equation बन गई, यही है ना, ठीक है. Then क्या था कि I have just rearranged this equation, ठीक है, जब मैंने रीअरेंज की, सो नंबर ऑफ मॉलिक्यूल्स इन अ सैंपल would be equal to small n into या number of moles into Avogadro number, ठीक है. So I just put this value, ठीक है. कैसे पुट किए, अब मैं I multiplied number of moles जो हैं यहाँ पे मैंने टॉप इक्वेशन के साथ मल्टीप्लाई कर दिए, ठीक है, ऑन राइट हैंड साइड एंड लेफ्ट हैंड साइड, यानी स्मॉल एन आर इज इक्वल टू स्मॉल एन के एन ए. तो स्मॉल, चले मैं दोबारा लिख देता हूँ बेटा आपको यहाँ पे, एक सेकेंड, ताकि आपको मजीद कंफ्यूजन ना हो. यानी मैंने आई जस्ट मल्टीप्लाइड द टॉप इक्वेशन विद ऐसे, ठीक है. कैन आई राइट इट, क्योंकि आई हैव मल्टीप्लाइड ऑन द बोथ साइड्स ऑफ द इक्वेशन, सो इट इज नॉट मेकिंग एनी इंपैक्ट ओवरऑल ऑन द इक्वेशन, ठीक है. सो आपके पास स्मॉल एन और कैपिटल एन ए किसके बराबर आ रहे हैं? चले मैं दोबारा रीअरेंज कर देता हूं. बिल्कुल बेटा, हाँ, कैपिटल एन के. सो दिस इज हाउ इट वर्क्स, ठीक है. सो दिस इज हाउ वी गॉट आवर इक्वेशन. इज इट क्लियर बेटा?
यस सर.
जी सर.
ओके, चलें, जस्ट होल्ड ऑन अ सेकंड बेटा. So putting these values, ठीक है, मतलब this value we just put it in the ideal gas law, which is on the 19.5. So small n r जो है number of moles into gas constant, ठीक है, it would be equal to what? This one, ठीक है. So क्या हो गया? We can write ideal gas law, this one. If I will give you an MCQs, I will give you like, okay, PV is equal to nRT. What is the correct equation for the ideal gas law? So PV is equal to nRT or PV is equal to nKT. So obviously the answer is K, मतलब both are the same equations for the ideal gas law, ठीक है. अच्छा, अब यहाँ पे the microscopic behavior को उसने explain किया हुआ है. So I think you have seen this example in FSC. देखी हुई है आप लोगों ने, सुनी हुई है या नहीं? कोई जो कार्गो ट्रेन है या मालगाड़ी, और मतलब हम लोग कहते हैं जो यूजुअली ट्रांसपोर्ट करती है ऑयल को, आपने देखे होंगे वो जो है कंटेनर्स ऑयल वाले, जो जब ट्रेन ऑयल ट्रांसफर कर रही होती है, सिलेंड्रिकल टाइप.
यस सर.
देखे हुए हैं?
यस सर.
जी
यस सर. आई थिंक ये वही एग्जांपल है जिसमें इसके अंदर वैक्यूम क्रिएट हो गया था.
वैक्यूम क्रिएट हो गया था, ठीक है. सो दिस इज द सेम एग्जांपल, ठीक है. और इसका मतलब है आप लोगों को पता है, मुझे बताने की जरूरत भी नहीं है, लाइक बच्चे हैं आप लोग.
सर आप बता दें फिर भी.
यार इट इज जस्ट लाइक सिंपल सी है कि लेट्स सपोज के उसने एग्जांपल इस तरह दिया कि देयर वाज ए सिलेंडर, ठीक है, ऑयल सिलेंडर था या गैस सिलेंडर, गैसेस मूव करते हैं इस तरह के सिलेंडर में, ट्रकों के पीछे देखा होगा आपने. तो नॉर्मली क्या होता है कि ठीक है, अब आपके जो गैस मॉलिक्यूल्स हैं, ठीक है, दे विल हैव हाई प्रेशर, ठीक है. आपके पास अगेन नॉर्मल लाइफ से मैं आपको टायर की एग्जांपल देता हूँ. इफ यू हैव ए टायर, ठीक है, एंड नॉर्मली आप लोगों ने देखा होगा कि इट्स प्रेशर डिक्रीजेस ड्यूरिंग द विंटर्स, ठीक है.
यस.
इफ यू आर, कैसे कि इफ यू फिल द गैस, ठीक है, and at the night, let's suppose if you are moving to the mug at the night, क्या होता है कि temperature falls to a very low value. So do you think it would have the same pressure like it was in the Lahore?
नो सर.
नो सर.
नो सर.
Pressure क्या decrease करेगा? Why it decreases? Because basically the pressure is the force per unit area, okay. So obviously when you fill the tire with the air pressure at the Lahore, so the temperature was higher, ठीक है. So when the temperature was higher, so obviously gas molecules have higher kinetic energy, so they were striking the walls, and obviously they will have a certain pressure. So when you will move toward the higher altitudes, like you are going to the Murray or the colder regions, okay, so at the night temperature falls a lot. So at that time, what will happen that the kinetic energy of the atoms will decrease because were not maintaining the temperature there. It is the process within the gas, tire gas is not isothermal process. Okay? So in isothermal process, what happens? No heat enters into the system or leaves the system. So in colder region, obviously the temperature will fall. So as a result, the kinetic energy of the atoms or the molecules will decrease. And as a result, what will happen? That its pressure, any force per unit area or the force that it was exerting on the walls of the tire will decrease. So when it will decrease, so obviously tire pressure will decrease. So in the same scenario, okay, they are saying that there was एक सेकंड बेटा अच्छा ठीक है अच्छा अक्सर टेक्स्ट कर देते हैं अक्सर टेक्स्ट नहीं करते इन बॉक्स में काइंडली बेटा कर दिया करे मुझे भी थोड़ी सी इजीनेस हो जाती है अच्छा अटेंडेंस लगाने में अच्छा नो ही सेइंग के दिस वाज अ गैस कंटेनर ठीक है सो गैस कंटेनर में क्या होता है कि ऑब्वियसली व्हेन यू हैव अ गैस कंटेनर देयर एग्जिस्ट द गैस सो व्हाट हैपेंड दैट a group of men basically cleaned the interior of this chamber, okay, and they cleaned it with this steam, okay. So on their way out of the cylinder, okay, they closed all the valves and all the openings, okay, and when they closed it, okay, at that time nothing happened. But at the night, because they were using with the steam, so steam has the same pressure as that of the atmospheric pressure internally, when they were doing it. So at the night, what happened that when temperature falls and the steam loses its energy, so at that time the density of the gases becomes very low. Okay, so it means that again the kinetic energy of the atoms also decreases, so the force or the pressure they were exerting on the wall from the inner side, it decreases while the outer atmospheric pressure increases, so it basically crushed the chamber. So in order to avoid this situation, what they have to do is that they have to open the valves. So when there was a gas required, so it can enter from the atmosphere, air can enter from the atmosphere into the chamber in order to maintain the overall pressure from the inside and the outside. So is it clear beta, k should I explain again?
सर एक दफा दोबारा समझा दो